Hello, welcome. So, here we are again. I'll be honest with you. I just want a project that gets me making videos again. I keep getting hung up on, trying to put lots of polish into a video so it's just perfect or just getting hung up on editing and the fact that I don't really like it. Things like that. So, I think what I really need is a video series that just gets the juices flowing again. So as a result, I'm not going to edit this very well. I hope you can understand. I just got to get over that procrastination hump thing that happens sometimes and just create something again. So here I am. I'm going to run it through an auto editor that will kind of tighten up my speech and speed up some of the coding sequences. So it won't be terrible, but you might want to watch this on 2x speed. I'll say it's optimized for 2x speed, put it that way. So let's create a compiler for my CPU. If you've watched my channel before, you'll know that I've been working on a CPU, and hopefully I'll get back into the swing of things and want to continue that project. But in the meantime, I'd like to write a compiler. And I was originally going to write this in Go, but overwhelmingly people voted for C. Well, C or C++. I'm guessing some people were voting for C++, but I'm not going to do C++. I know it was C or C++. I remember a bit of C. I don't remember very much of C++, so it is what it is. So the last time I really seriously wrote C was when I was a kid. So this is going to be interesting. I remember a surprising amount of C. I think it's one of those languages that I'll probably never forget because I learned it so young. So yeah, I was 9 when I learned C, and somehow I managed to learn it from some old compiler manuals, Turbo C++, no less, from Borland. So yeah, that's a long time ago. I think that was running on Windows 3.11, or maybe it was even in DOS. I don't really remember. I know I was mostly using DOS at the time. But anyway, ancient history now. So, a compiler. Yeah, this is going to be kind of interesting. I've been kind of obsessing with how to create a simple compiler for a while. I've made a few attempts at doing it in Go with limited success. Part of the issue with Go is that people just don't seem to like it very much. I absolutely love Go. Go is my favorite language. I've been writing Go since 2009. Basically, as soon as Google released Go, I started learning it. And I absolutely love the simplicity of Go. I can see that it probably rubs some people the wrong way, and there's a few rough edges that I wish were better, but yeah, I haven't really played around with a language that I like quite as much as Go. Yeah, I like boring languages. But, I've been really enjoying C. As part of preparing for this video, I've been writing an emulator for my processor. I might as well show you around a little bit. So, here we are. And here's the emulator. I will probably be writing C as if I'm a Go programmer. And that's just how it's going to be. I have a lot of catching up to do to get back into the groove of what's the latest ways of writing C. And I believe the last time that I wrote C, C99 might have been a thing, but I think I was writing C89. So yeah, because it was early 90s or maybe mid 90s that I learned C. So anyway, so what do we have here? We've got an emulator. I just went ahead and wrote an emulator because it's kind of off topic for writing a compiler, but I'm going to need an emulator if I want to target my CPU. And I think it's going to be simpler just to target my CPU and not try and target x86 or something like that. RJ32 is a word-oriented processor. which means it doesn't really have a concept of a byte. Bytes and words are the same size, and they're both 16 bits. That poses a problem for a surprising majority of compilers. I think LLVM can handle it, but LLVM, I think, is at least 2 million lines of code, if not like 10 million lines of code. So, yeah, I don't have months of reading code, dense C++, no less, before I can even start. I can't get myself into LLVM. I have tried. Maybe if someone wants to pay me to get into LLVM, that might be a different story. But yeah, for now, I haven't gotten into it. I have found a surprising number of C projects that can be very helpful on this journey. But first, I guess I was going to show you around here. I mean, it's an emulator. I mean, here's the CPU. This is where all of the major state happens. So you've got your register file, you've got the data bus is something called an IO bus, and that's in the bus files here, how that's defined. I've got a program counter, I've got program memory, and what's interesting is I pre-decode the instruction formats. I think there's like 6 or 7 different instruction formats for RJ32, and it's just faster if I just go through all of program memory and decode the entire thing into 32-bit instructions rather than 16-bit instructions. And that just makes this thing lightning fast. I think the Go version, so this is just a port of my Go version to C. The Go version was something like it ran at something like 400 megahertz. I'm guessing the C version runs way faster than that because there's no garbage collector or anything, although the Go version didn't really use the garbage collector either. But yeah, so we've got that, and then there's some initialization. And again, I'm writing this as if I'm a Go programmer writing C, so my apologies, but that's just how it's going to be. I even set up the C auto formatter and everything because I'm just so used to writing Go code. But yeah, anyway. So yeah, we've got some tracing that's happening here. We've got, this is the main entry point. So this can be run by the compiler directly. So I haven't set that up yet, but that should be straightforward to set up. And we've got the instruction encodings. I think that's in the H file here. Yeah, so I'm loving this syntax. I don't think that was around last time I did C. So this is just the raw instruction, and all of the instruction formats is just put into a big union here. And of course, I'm heavily using bit fields because I wish that was something Go had. So yeah, each of the instruction formats, and then we've got the raw instruction, so I can just assign it here, and then I can pull out the raw bits. Here's here's the decoded version of the same thing. Yeah. You can go through this on your own time if it's interesting to you. Feel complete freedom to take this code and do with it what you please. There is an MIT license. This is just mainly here to protect me. Feel free to just take this and run with it. I know there's this here. Again, that's just there to protect me. I don't mind if you take this code and port it over to your own processor and run with it. Go for it. You don't even have to cite me, although the license says you should. Just add your name above here and just copy this. Copy this and your name here. Or put it above if you prefer. Doesn't matter. Go nuts. So, what else to say here? I think that's it. I'm starting to ramble. I'm sorry. There's a test file here. This is copied from ChibiCC, and I might as well show you around there. ChibiCC is a very simple C compiler. and the code gen is really straightforward. So if you're wanting most of the compiler done already, ChibiCC might be a really good option for you. It's set up rather interestingly in that the commit history, and if you go all the way back to the very beginning, there should be a link to it here. First commit, here we go. And then down here, somebody helpfully put in the commit tree here. So if you go down to the very beginning, it shows you like step by step exactly how to build a C compiler. It's an amazing resource. Yes, it's written in C, but I've successfully followed this in Go, and I'm sure in whatever your favorite language is, you could probably also follow this. C is really straightforward. Wow. It's got its quirks, like any language, but you can figure out what's going on, and this has been really well polished and written. He was going to build a book out of this resource. It's right here, what he has completed anyway. It's in Japanese, but you can just translate to English. And I haven't read through all of this. I don't know how complete it is. The automated translation tools are not the greatest yet. So I have a hard time reading like translated content, but if you know Japanese, this would be an amazing resource. I don't know if this is like partially translated or if some of it's in English or what. Yeah, I think it's just partially. Weird. Anyway, it's taking a really long time for the translation service for some reason. So what was I going to say here? ChibiCC, yes. So this is an excellent resource. There's also this one. This is also a C compiler, and it's designed specifically to make it really easy to convert to a ton of other languages. Interesting thing about this one, my cat can't figure out how to open the door. Just push, Rosie. Hold on. I know I'm not going to edit this, so. Now, hopefully my cat doesn't decide to jump all over the computer and do all kinds of crazy stuff. Okay, so yeah, this one is interesting because it has one-to-one correspondence. Let me see if I can find it here. Internals. Here. It is also word-oriented, which is very, very interesting. So pointers, integers, and characters are all one byte, so to speak, or word, or whatever you want to say. So they're all the same size. That would make this really easy to port to RJ32, since this is also true for RJ32. So this is also quite interesting. It's already got an intermediate language, which is awesome, or an IR, intermediate representation, I should say. It's already a Harvard architecture, so also very interesting, although it only has 6 registers. That's actually all you need. So if you're looking for like a super, super, super simple CPU to build, targeting something like this is actually quite interesting because these are the only instructions that you need. So yeah. So yeah, there's this one. I haven't looked through the code, but I presume it's also quite straightforward and easy. What else was I going to say? Oh yeah, for the compiler that I'm building, you're going to need an assembler. And I'm just going to use custom ASM because I don't really feel like building an assembler right now, but building an assembler is not hard, and it would release some of the limitations that I'll get into eventually. Probably not in this episode, but I'll talk about some of the limitations of this program as far as writing a compiler for it is concerned. So I think that's all I wanted to cover in the browser window here. So what are we going to do? I guess I probably could have covered this first. Well, we're going to write a C compiler in C. We're going to do it incrementally, just like chibicc. By incrementally, I mean rather than going horizontally, where we build first a lexer, then a parser, then a type checker, discover that type checking is really, really difficult when you try and type check an entire language all at once and then give up, which is what happens to 99% or more of compilers out there that are hobby made. Instead of doing it that way, what we're going to do is we're going to take a slice all the way from the source code all the way to compiling the program. And that's how chibicc is built. So we're going to be using that kind of as a scaffold to inspire us in that direction. I'm not going to copy chibicc because they spent probably hundreds, if not thousands of hours developing that code base and meticulously crafting it. If I just ripped that off and made videos on it, I would not feel very good about myself. So we're going to go a different direction. But we're going to take that approach because I think that's a much better approach, because in the case of the type checker, when we get to type checking, we're just checking the feature that we just implemented. We're not type checking an entire language. And so swallowing the pill that is type checking is a lot easier in small doses. Anyway, so we're going to build it incrementally. The other thing that I really want to do, and this is so that I can differentiate from just completely ripping off chibicc, is data-oriented design. We're going to do a data-oriented design. In other words, we're going to try and bake in the best possible chance for performance from the very beginning. We're not going to go all out and do a single pass compiler. That would be the fastest compiler that you can make, but we're going to do a data-oriented design, and I'm actually really excited to show how that works and what you can do with it. It's a really neat idea. It's from Carbon and also Zig. So the folks building Carbon have a video on the data-oriented design of a compiler. I forget the name of the guy, but I'm sure you can find it if you just Google Carbon data-oriented design compiler, and you'll find it. Zig, Andrew Kelly from Zig, also has a bunch of videos on data-oriented design for the Zig compiler. Some of them are not on YouTube, they're on a different platform, but I believe you can find them by looking for I think it's the software you can love. Anyway, I'm sure you can ask around in their community. They can tell you where to find those videos. Some of them are on the platform Vimeo. Some of them are on Vimeo. Some of them are on other platforms. So it takes a little bit of digging, but I'm sure you'll find it. The next thing that I would like to do is, there's no IR or SSA form done in chibicc. It purely stays with a abstract syntax tree, and it doesn't go any further. So there's no register allocator, there's no nothing like that, which is partly why it only needs 6 registers, right? So we're going to do a register allocator with an SSA backend. So, and I'm excited to share my knowledge of, all of the research rabbit holes that I went down on all of that stuff, and what I think is kind of the simplest way to do this. So it will have some optimizations. So the vast majority of bang for buck will be gotten out of the register allocator. That's like the number one best optimization you can implement if you're only going to implement a few. But we're going to be able to implement a few more than that just by doing some people optimization, something called hash consing, or it's also called global value numbering. They're actually kind of the same thing. Hash consing might be a little bit easier to understand when it's explained from that direction, whereas academic literature usually goes through global value numbering, which is kind of a confusing concept until you realize they're just memoizing objects and reusing them. And that's all that is. Like, why do they have to explain it so difficultly? And yeah, so hopefully I can simplify a few academic concepts. That's kind of the goal of this. Compilers are wrapped in mystery, and most people think that they're extremely difficult to make and extremely difficult to do well. And they are mainly because most of the documentation is academic in general. In like, how do I say this politely? Sometimes academia is kind of about proving that you're smart to other academics rather than trying to get across the idea, if that makes sense. And I think it's not necessarily that that's done on purpose, that's just kind of the culture of academia. Like, there's just kind of this culture of puffing up your chest and using big words. So hopefully I don't like offend anyone. I hope that's blatantly obvious to most people that that's what goes on there. But to the few people that I probably did offend, I'm sorry. Maybe you're not that way, but your colleagues probably are. So I'm not talking about you. I'm talking about just in general with like a big, broad paintbrush. And I know that there's tons of academics that really value teaching and really enjoy teaching and making things simple and helping people to understand. Yeah, maybe I'll just cut out that rant entirely, or maybe I'll leave it just for giggles. Anyway, so let's see. I have been rambling for 26 minutes. Hopefully it's a lot shorter for you because of the auto editing and all of that. So I just kind of want to get into building something. So let's try and do that. So the first video is not gonna be a whole heck of a lot. I think the makefile is wanting me to call it this. What should we do? Well, the way that ChibiCC starts out is getting a program that returns a number as the error value and just going from there. So the smallest possible program would be int main return 42. That is the smallest possible program, really. And so how could we compile this? Well, I'm not wanting to get into tokenization and lexing and parsing and all of that quite yet. So we could really just strip this down to, since we're defining language, right? Just this. How do we compile this and produce the code that the C program would produce? Well, in quite a lot of assembly languages, this is all it is. It's just ret 42, although usually there's like a move or MV, I think, a 042, and then ret. So this is basically the assembly program that we need. I believe this is valid RJ32, although, you know, it's been a couple of years since I really was in that project. So let's see if we can build this program. So I guess we need to include standard I/O. Sure. I'm not using Copilot, I'm using Codium, but I will be using AI assistants because, well, that's the future, and I want to get good at it and practice, practice, practice. So with this, we need to produce the text of the program. So I guess, and then there we go. So let's just just take the command line argument. 0 is the name of the executable, so we want 1, which is the name of the first argument. And we want to move that into the A0 register, which the emulator will use to return the current value. The other thing that we need to do, and I kind of lied about returning, we actually need to error, and that's because the A0 register is not used as the exit value from the emulator unless there's an error. Otherwise it's 0, because 0 means it didn't fail. So if you hit the halt instruction like that, then it'll just return 0. It won't return what's in the A0 register, which is what we want it to do. So error it is, even though it's not an error, but that's the program that we need to produce. So I think this is everything. Terminal, there we go. And I have a test.sh, which I got from ChibiCC. It's basically a copy and paste of ChibiCC, except that I changed these lines here, well, specifically these ones. So what it's going to do is it's going to run Gauzy and put the output into temp.asm. Then it's going to use custom ASM to compile a binary ROM. And I'm using the CPU def, which is a copy and modernization of the one in the RJ32 repository. And then we're going to just run the ROM through the emulator. So let's make Gauzy. Did that work? Huh. Where did it get those lines from? Where did this come from? That's weird. Am I in a weird directory? No. Here. So here's this. Obviously we don't want just null there. But that does work there. Okay. Let's go. It doesn't like that syntax. Why not? Oh, because I didn't call it MV. I called it move. Move. I think that's correct. Oh, I got a segmentation fault. I think that's to be expected because there's nothing to load. Make Gauzy. Expected 0 got 1. Oh, that's it. I think I know why. Yeah, it's this right here. So, obviously this is not scripted. So, the... Okay, that looks like it worked. We could use line feeds between these. Let's see here. I think you have to go echo-n. Or maybe we do echo-n up here. Don't have auto formatting in here. All right. That better? No, it's not. And it's not what I think it is. Typo. There we go. Yeah, that's what I'm wanting. Yeah. And then an echo after here. There we go. That's looking good. So I do have it emitting tracing information by default. That's a little distracting, but at least then we know what it's doing exactly. ignore this. It's because the error code doesn't have a proper format. I guess I could fix that. Where is that? Here, I think. That looks like what I want. Probably a better way to do that. I think I can just go make -c or something like that, but whatever. All right. Yeah, I guess I could have got rid of this as well. But anyway, that is looking correct, despite it producing an error, but that's okay. So that is kind of the basics of step one. I took some of the effort out by having this prepared. I kind of don't want the first video to be too long, but I mean, this is really not very much. Let's see, what's step two? Add and subtract. How do we do that? All right, this looks pretty straightforward. Yeah, we can probably do this. Yeah, let me see if I can remember well enough to do that in here. So they're moving the... What are they using to split? Oh, they're just... Okay. So I'm guessing stir to L is doing most of the parsing. It's just parsing until it finds no more numbers. And that's all they're doing. Oh, and then it returns P for... Oh, okay. Cool. Yeah, that makes sense. Okay. So then... B's not a very good variable name. Let's call it stir equal rb1. And then we've got stir to L, which is not included. And stir base 10, and then stir to L, I think it's probably in string. Is it in string? LD, I got. That looks correct. I don't know what to do with this. I guess because it's... yeah, that seems to make it happy. I have linters on because that's what I'm used to from Go. So I'm just trying to obey the linter, hoping that it'll catch bugs before they happen. So this should be the same and it should pass the test. Yes, it does. Oh wait, I didn't make it. Make Gauzy and... all right. And then we can continue from there, I think. Wow. So I'm guessing probably know this, but 0 is false in C. So when it's doing this, it's looking for the 0 terminator. Strings are 0 terminated in C, so that's how that works. It looks a little strange if you're used to a different language, like you can't do that in JavaScript or Go generally. And you probably couldn't do that in Rust either because it's not safe. This is perfectly safe as long as there's a 0 terminator. If there's no 0 terminator, then obviously it's not safe. Let's see. So it's expecting a... minus or a plus. And then, of course, cases fall through in C. They do not in Go. Move into A1. The next character, and then we add. Or no, we subtract. Yeah. A0, 1, A1 from 0. And then the same thing for add. All right. This should in theory work. So let's see. It compiles. 1 plus 2 plus 9. Correct? Minus 2. That looks correct. Let's see. Let's add some test cases here. The first, is it expected is on the left? Okay. Let's see. 5 plus 20 is 25 minus 4 is 21. Yes. That should work. That will not. It's not skipping white space yet. That happens in the future. So let's see. This is not much different. I'm gonna go like this. And little AI save me math. Let's see. So 34 minus 12 is 22. So negative 22 plus 5 is minus. I don't think minus will work. So we might need to do. No. Let's say 14. So then that would be minus 2. So this should be 3. Let's see. That seems to work. Excellent. So we've got the first 2 steps done, which is a little further than I was expecting to go. I don't think, well, at 2x speed, I'm trying to keep it under 40 minutes. So we could potentially go a little further. The next step, I think, is introducing a tokenizer. Let me check. Tokenizer, yes. That is maybe a bit more than I kind of want to do in the first episode. Yeah. Quite a bit more than I want to do in the first episode. That sounds like an excellent thing to do next episode. So, thank you very much for watching. If you feel like you're grateful in any way, I'm sure you can figure out how to express that gratitude. I'm not going to tell you what to do. There's enough people telling you what to do these days. So I hope you have a wonderful day, and I'm not telling you what to do. You have a wonderful day if you feel like it, but I hope you do feel like it. Yeah. I will see you next time. Bye.